Hey everybody, we're going to get started. Thank you all for coming. So this is NLSea. It's an NLP meetup for Seattle. I decided not to. It's a small space. It'll be okay. And yeah, tonight we're going to talk about Subword Tokenization. But first, about NLSea a little bit. The goal is to share knowledge about practical and modern applications of NLP. So this is people talking about cool things they've done, talking about modern techniques like Subword Tokenization, etc. And also, I'm just looking for ways that we can make this more useful for you guys. So if you have ideas, feel free to just blurt them out there. And also, hopefully this talk can be a bit involved. If you have questions, definitely raise your hand or comments, that kind of stuff. We do have a code of conduct. It's puppies. And it's honestly, it's really short. That sounds like something that's long. It's not. But in short, just be nice to each other. Invest in each other. Like, this is a community. Do stuff to help other people out. Don't be a jerk. And we have a Slack channel, if you didn't know. If you're not on the puppy Slack, I posted a link in the Meetup on the Meetup page. And it's NLSea on there, so that's pretty, Thank you for One Piece for hosting. They're awesome, and I figured I'd give them a chance to talk about it.
Stuart actually is our first member of Seattle location. So yes, we have 10 locations around the globe, like 5 in the Bay Area. We're coming from we are based in the Bay Area. So One Piece Work is actually a tech community that can provide funding, office spaces, and connections to all those tech entrepreneurs or people from the tech world. So this is what we do. We have 10 locations, 5 in the Bay, 2 in LA, 1 in Seattle, 1 in Shenzhen, China, 1 in Shanghai, China. So all we do is we want to build a tech community so that we can help all those tech entrepreneurs or tech engineers and better achieve help them to achieve their goal. Yes, this is cool. Thank you so much. If you need anything, just my name's Chen. I'm the partner of One Piece. So let me know.
It's a great place.
Thank you.
And definitely also important, if you have a talk you want to give or something related to NLP that you want to look into, definitely I'm hoping other people can get involved and give talks too. It can be intimidating, of course, but really it's not that bad. And the process of preparing the talk, you get to really look into stuff, and it's super interesting. So definitely, even if you just feel like a little bit, just mention it, and I will pat you on the back and get you excited. And if you need to bounce any ideas off me, just let me know. We want other speakers. It gets lonely up here. Yeah. So with that, I'm just going to go switch on to the talk, Subword Tokenization. And there is a terrible joke about tokens inside your tokens, so I'm sorry. So I'm Stuart. I make a thing called Tag It. It helps you identify topics inside text. So not quite topic modeling, but mostly text classification. So you can just go tag stuff on there, and it learns to identify it for you. I actually just launched recently, so you can actually get the high quality neural models, and you can have private topics. You can have team moderation tools, etc. So go check it out. I also do some consulting via Thought Vector, so if you need something more bespoke, just come talk to me later. Or if you just want to talk about NLP, honestly. But didn't come here to talk about that. Came here to talk about Subword Tokenization. So to walk through that, we're going to start with sort of a little refresher on what is tokenization. Talk about why you really do it, in the abstract. The challenges that you have tokenizing real-world data, because there's, some of us are dealing with data that's coming from very bad sources, I'll say. Not bad people, just bad input methods. And talk about strategies for using Subword Tokenization to address that stuff. Talk about some different strategies in use today. And then at the end, we're going to implement a Byte pair encoding tokenizer, which is kind of the emerging winner that I've seen. So yeah, let's jump into it. Tokenization, what's that again? So it's really just turning, in the simplest words, it's turning a string into a list by deciding, okay, these are the items in the string that are significant. So that could be words. That's the most common one. Could be letters. Could be all kinds of stuff, right? But it's not sequence mapping. You're not turning in integers just yet. But you can. This is sort of the plain Python example of that turns into that, and it goes eventually down into some model. And to like abstract it a little bit, because it's not just text that you tokenize. There's other applications like chemical equations. I think bioinformatics, they do some tokenization there. You've got these different symbols coming in sequence, and the sequence is meaningful. And you do some grouping of those to make it a smaller sequence, right? You're changing the dial on your vocab size versus your sequence length. And you might ask, well, why do that? I thought more dimensions made it harder. And actually, that's really useful because having a shorter sequence to make predictions on makes it much easier, right? You don't have to remember as much stuff in this sequence of information that you're handling. You can imagine, like, the words that I'm saying right now, it's a bunch of strings of sounds that I'm producing, these pressure waves. But our words, or our brain reconstructs them into a sequence of words that each has a specific meaning, right? And if we were just listening just straight to maybe I can't make that argument, but
well, if you're thinking of the letters of every word when you're sort of speaking to you, but
yeah, and it gets much easier once you learn to recognize words, right? Like if you've learned a new language, when you learn to identify those word boundaries, it gets so much easier. Anyway, so there's moving from that like character space to like a word space, as it were, so that each of those words has specific meaning, right? Crash, really, you feel like someone says that and like your brain immediately is like, it's that. The letter S is in like most of the dictionary, so not that useful. So yes, we're reducing intertokens reference length, mapping to like a larger, more meaningful, semantically rich, more semantically rich space. And by doing that, we're reducing the burden on the downstream model, like an RNN or even some linear classifier that's looking at like TF-IDF vectorization of this. So imagine TF-IDF with just characters, right? So that being said, there are some challenges in tokenizing real-world data. Like if you're just pulling out NLTK and you're just, give me some tokenization, you get things like misspellings or even intentional misspellings, adding emphasis, adding extra letters in there. You get super with 5 U's and 2 E's, right? Or 2 R's. You have languages that aren't separated by white space, right? That's Japanese. It's koreo dono yo ni token ka suru no desu ka, which is, how do I tokenize this, right? And there's no spaces, right? Where are the word boundaries? We can't tell. But they're there, right? There are specific words in there. Also, when you're building vocabs from your unlabeled data, your vocab size explodes, and you essentially have to decide at what point do we just start ignoring new words. And you can imagine how many different ways can you add emphasis to the word super, right? I was super late, or I was super late, et cetera, right? You add misspellings in there, it's terrible. What do we do about it? Subword tokenization. And it's this idea that we instead want to be able to learn our tokenization from the data itself and not use these heuristics that we identified, right? Like if you look before, the way that we would tokenize this is by saying, oh, I know that spaces in this language separate words. I know that punctuation should be separated, like specific kinds of punctuation, but not some of them, not apostrophes in some cases. And we build this like set of rules to tokenize this one specific language, and then you go to a different one, and it's suddenly you have to create new ones, right? Not to mention all the misspelling stuff. So we want to figure out a tokenization strategy that utilizes some of our intuition about language, that isn't language specific, and can deal with some of these naturally occurring patterns in language that humans recognize but are really difficult to encode in computers. So this kind of relies on the idea that that like words are made of common chunks, and that those common chunks can be put back together and represent the word, and that a model can use that to understand it. So for instance, unfriendly is, someone's unfriendly. And it's kind of obvious how to segment that one. You would say un, that negates it, and then friend, right? That's, friend. It's like one of the most common words. And ly, which, makes it into like an adjective. So we can see how a model would take this sequence in and get to the right understanding of the word without having to have the word unfriendly or learn what that one specifically means. So just to enumerate them really specifically, we want to remove language-specific heuristics like white space separation. We want to prevent out-of-vocab problems that happen from the crazy explosion of different ways people write stuff. And we want to, in an unsupervised fashion, learn the most meaningful tokens directly from our data without having to do anything special. So let's just start with something really basic. What if we just take the characters? I know I said that was dumb, and it kind of is, but you can still do it, right? It will limit your vocab size. I've got this data set of building of like reviews for businesses worldwide, and there's a lot of them, and it spans the whole world. And there's only just shy of 10,000 different characters used in the whole thing. So you could construct a tiny vocab from that relative to other things. Like if you look at word vocabs out there for word tokenizers, people are using hundreds of thousands, millions, and this thing is much, much smaller. So it's fast, but the downstream model do have to do work to recreate that meaning, to observe these characters in sequence and know, okay, this is referencing this word, and to remember that when it's at the end of the sentence and it needs to remember this long-term reference. That's actually one of the big challenges in handling sequence data, is being able to know which data to remember, and not like store in memory, but to store in this hidden state inside the RNN so that it gets updated in the right way so that it remembers something from the start of the sentence that's relevant when it's reading the word at the end. And our brains just kind of do it naturally. So we want to keep sequence length short, which this doesn't do, but we don't get out of vocab problems. There are some notable uses of this. First, Karpathy's KRNN was like the first character language model that really showed awesome results. He posted a blog post on that, which is linked. This whole presentation you guys will be able to get to later, by the way. And it really showed that you could do character level language modeling, and I'd like to think that that kind of paved the way for people to taking language modeling more seriously, language model pre-training, that kind of stuff. I think it was like 5 years ago, so it's not state of the art anymore. But OpenAI's NLSea was also character level, and it essentially just looked at character by character, and it had this trick where I think it did multiplies instead of adds. But it let them provide a state-of-the-art model for sentiment, trained on very sparse data, simply because they found that with character-level language modeling, they could just pour in so much data that it just had to learn about sentiment, and that the problem of labeling sentiment after that was trivial once it understood it. So that one had a lot of parameters. You didn't really want to run it. I think I wanted to use it to build a data set with in-domain data at some point, and you'd say model.predicts 3 sentences, and half a second later you would get the answer. So it was heavy. So there's got to be a better way. And that gets to byte pair encoding. This one seems to be the middle of the road strategy for subword tokenization, and this sort of language ambiguous tokenization that we're trying to do. And that's primarily because of the strategy it uses for actually tokenizing once you've learned the vocab. And I'll talk about how you learn the vocab after just going through this example. But essentially, you assume that you've already learned this vocab of meaningful subword units, UN for unfriendly that we talked about before. And what it does is it goes through the string, And from the start, it looks at, okay, what is the longest substring there that is actually in the vocab? And then it emits the token for that, and then just moves on. So you've got 4 things there, that's a subword unit. You've got 3 things there, that's a subword unit. For that blue one, I don't know, somehow there's no longer word there, but we just emit that one token. And then somehow maybe that's a phrase or something, I don't know. This is totally constructed. So, but you end up with a much smaller thing that is a much smaller sequence via vocab that's learned based on the data and can be computed quickly, but doesn't have any of those heuristics that we normally use to tokenize stuff. So, originally data compression algorithm. Byte pair encoding actually was just a way to, the idea was, well, if we should just count byte pairs, and if we want to compress a file, then we figure out the most common byte pairs and replace those with a different byte that's unused or maybe something longer. And then we can just ship the compressed thing with a vocab, and on the other side it'll just do the opposite of it, right? And then information theory is a great analogy for machine learning for me, and I love it. And looking at data compression algorithms for inspiration and how to how do we intelligently group data is the coolest. But yeah. So essentially, if you want to learn a vocab for this, it's not very complicated. You just scan windows over your data. So you're looking at n-grams, 1 grams, 2 grams, pi grams, or that's also 2 gram, up to your max n-gram, whatever it is, and just count them. And then based on some scoring of those, usually you just look at the count. You cut off the least informative ones until you reach your vocab size. So it's really simple to learn a BPE vocab, and it's also really simple to encode with it. So it's a very simple strategy, and it lets you not have those heuristics about data that we talked about. And it's fast. This is never going to be the slowest part of your NLP pipeline unless you've done something wrong. That said, the greedy algorithm does get things wrong. Unfriendly, for example, is obviously you want to split the un off the front, but it might have seen, unfried or something else like that and decided that UNFR was a subword unit also, and then that'll get replaced. So you don't always get the ideal or correct tokenization, but you do get consistently good results. Yes. So this is an example of where these strategies can be really useful for non-text data. This is a friend of mine from Tokyo that he was working at a research institute over there, and they were doing, it's like corporate R&D, never mind. It's like consulting. It's weird. Anyway, they were doing something on chemical reactions to predict reaction rates, and they were just using character tokenization before, and they switched to this this trivial BP implementation I made, and it literally doubled their accuracy, which is, to me, is unheard of. I could imagine having error, but doubling accuracy is, so try BPE. It's worth it. To give even more proof, I don't know if you've heard of these models, but BERT and all of its derivatives use BPE. GPT-2, and also I'm not sure I know of any neural machine translation models that don't use byte pair encoding, but I'm not an expert in machine translation, so take that with a grain of salt. And there's one more just really cool one that I couldn't not talk about because the perspective that it takes on tokenization is just, in reading it, it really helped me understand the problem a bit more, the problem space a bit more. Poignant pause later. The SentencePiece is some research that either came out of someone that got hired by Google or in part of the process, I'm not quite sure. It's an @Google address, so. But the idea was that these word boundaries or subword boundaries are a bit ambiguous, and they seem to be noisy, right? This idea that you can get a different tokenization of a word with BPE depending on where it happens in the string, that sounds bad, one. But the researcher thought about that and said, okay, well, if we just generate a bunch of different possible tokenizations using this BPE vocab, then we can effectively sample inside that space, and that can be noise that is that we then use to regularize the downstream model. So you can say, okay, even if it says unfriendly and it's tokenized wrong, and there's unfriendly and it's subword tokenized right, those should get us the same answers, right? And that's really cool. That's one. That's not actually how this happens. But how this actually encodes is that it does that sampling of a bunch of different possible ways to break it up. And it uses a really simple language model to say which one of these is most likely. And it essentially just multiplies the likelihood of each of those tokens together, I think. And then the highest one wins. And then it outputs that. So that's really cool, and I really like that perspective on like the ambiguity of tokenizing something. This idea that there's not just one correct way, because it feels like every time I run into an NLP problem, and there's this temptation like, oh, we should correct spelling, or oh, we should lowercase everything, or we should do this thing to coerce the data, but in general, the person intended it to be that way. They wanted it to be all caps, right? Or that the fact they use 5 R's in super tells you something about that person. It tells you something about what they are thinking about the review they're leaving, right? So I love this perspective that you just want to, go to where the data is and try to figure out the right way to tokenize it. Stepping back from heaping praise onto this, it is really slow, which is sad, because you sample a bunch of possible tokenizations, evaluate which is the right one, then output that. This is going to be likely the slowest part in your NLP pipeline, even with the model, unless you're using a large model like BERT or something. But even then, I think that I was doing it was either 1 or 10,000 tokens per or words per core, which is super slow for tokenization for me. But that being said, you get the best tokenizations with this, and it is able to learn from unlabeled corpus, and it does really cool stuff. This is used by what's up?
Any way to parallelize it?
So I don't think so. I remember looking at the implementation in the paper and thinking oh wow, you couldn't put this on a GPU, but I also might be wrong. So, but this SentencePiece is also a library that you can just download. I think you just pip install SentencePiece, but it doesn't use GPU. So, so it is in use by XLNet. That did set some state-of-the-art stuff before it got overtaken by another BERT derivative, but that's how it goes these days. So I wanted to pause. Actually, if you guys had any questions before going on to the demo.
Yeah, I was just thinking, is there some sort of when finding the right token, is there some sort of a scoring assigned to kind of likely tokens that could be assigned to that specific pair or whatever sequence of characters? And then chooses the one with the highest similarity score?
You're talking about, so you have the tokens you've chosen already, and then looking at those, what's the most likely tokenization for the next one? I don't know if anyone's done that yet, but it sounds like a good strategy. I mean, at this point, I think there's an abstract framework that fits into, and that people haven't tried sort of each permutation there, but that's sort of sitting, I think, in between SentencePiece and BPE, and I think that's between there is a really good place to look at, because SentencePiece is obviously it goes a little bit too far, and they're what if we just try everything? But having that level of inference would probably be good.
One thing I missed was okay, so if you're building using BPE on a corpus that you have, and then you're going to build a model with that, but then you get other data that comes from outside the corpus.
Mm-hmm.
How do you handle characters you haven't seen before, or tokens you haven't seen before?
So with BPE, usually you make sure that essentially every character you're going to see, at least every single character, is in your vocab. And then the way that you prune stuff, if you're doing naive scoring, you're almost never going to prune a shorter version of something than a longer version. So the worst you can do is single character tokenization.
So they'll drop into single character, like for the where they're missing.
Yeah.
But ends up
Yeah.
Yeah.
So
Yeah. So I mean, for English, it's not really a problem, but like maybe for
So the big risk is places where you just don't have very much data, and that kind of you're going to have problems there because if you don't have enough data to, learn a BPE vocab, you probably don't have enough data to train a classifier or do some other interesting thing on it.
Yeah. So it's
but yeah,
not
that's
a problem because you should have enough data.
Yeah, I mean, I don't want it to just be to just have more data, but if your character if strings of characters like almost never show up in your training data, and you don't have some hole in how you're collecting that data or how you're choosing which data goes in there, then that's kind of an unavoidable problem. It's kind of like, well, what if there's an unknown unknown?
For the data where the SentencePiece where you try all the different possible tokenizations, and then use our language model to find the most likely path. Where does the language model come from? Because that is also dependent on tokenization.
Yeah.
To build.
Yeah, and it's not, the language model isn't something, it's not like BERT out there. I think it's really just looking at word frequencies or subword token frequencies, maybe in context.
Mm-hmm.
But it's something super simple. I was surprised by how simple it was, but it works. So it's like it's something like frequency over some other frequency. So
I was curious about some of the tokens you see with these models. Does it kind of break down phonetically, or is it just like QU, or how intelligible are these tokens that you get?
you definitely get things like QU or like LY or ING. But there's also definitely times when you find stuff that's like the first 6 characters of like 5 commonly used words or something, and you're like, okay, I see what you did there.
Mm-hmm.
And in the back of your mind, you wonder, like, I'm not sure if this is actually bad or not, because it could be broken down more. But if it provides the same information to the model, or if the downstream model gets that consistently, then I have trouble thinking that would be a problem.
Mm-hmm.
You're going to see some bad examples because the corpus I'm going to provide is really small. But then you're going to see a good example because the corpus provided is really big. It's just not going to be done real time. So,
Okay.
Anything else?
Could you, I mean, I'm curious to see the implementation, but before then, could you comment on like what people do, if anything, to use these techniques in less analytic languages? So, imagine a word, just long-range morphological changes to the word, depending on the stem or whatever. Is that in those situations, if that makes any sense, do people still get away with these techniques?
I'm not sure, but
Yeah, so I was thinking like Turkish, like you've
Yeah.
got like 2-way, 4-way vowel harmony. And so at least with that sort of like morphological rule, like your phonemes, you now have sort of naively 8 times more
Yeah.
sort of like things that you have to do, and which is not bad, but if you have more rules like that, eventually like exponentially, it would seem like either your size becomes large or you lose coverage because it's really the same sort of
Yeah.
phoneme, but like you don't have it in your data.
yeah.
So that wasn't a real question in the second part, but
I think that's a great question, honestly. And the only comment I haven't tried. The only comment I can make is that someone used that BPE vocabulary to tokenize Turkish, and I didn't follow up with them with how they reported a bug. So, but I fixed it. But I'd have to follow up with them about how it worked for them. Okay, I'll move on to this link is to an already completed one for people that come later, but I'm gonna do this live. Yeah?
No.
Oh, okay. So can you guys see this? This is an example. Like, can you guys read that text? Okay. I guess the better question is, can you not read that text? So just to talk a bit about the implementation, these tokenizers generally break down into, you want to generate, or the BPE tokenizer breaks down into you want to generate n-grams from your text, you want to count those n-grams, and you want to prune those counts because eventually, if you have a sizable data set or even a not very sizable data set, you're going to run into memory problems pretty quickly because the n-grams get quite long. So we're going to essentially write like 3 or 4 functions, being generate n-grams, count vocab, prune vocab, and encode, which is just going to do the tokenization for us. So Python makes all this stuff really easy. I'm just going to, there's only one thing we need to import from collections, import counter. If you didn't know about that, counter is like a dictionary that is a default oh yeah, I love it. But the counter, it's a default dict of integers that implicitly, you can just increment stuff and it'll create, it'll zero it before doing it if it doesn't exist. And it does some funny things with the constructor. I love it. Collections library is awesome. And we're going to use light type hints here. So generate, wow, how do you know about that? I deleted all the cells, so I should probably it doesn't matter. Actually, this is great. So I don't have to worry about the forgetting what should be in there.
But next time on NLSea, we'll do a IDE, predictive IDE plugin.
Yeah, there we go.
That's a thing. Like,
just search GitHub.
There is like some crazy stuff like this out there. Yeah.
All right, so we got.
That actually sounds like it works.
Oh.
Like for web developers, right? People are doing things where there's like commonly applying like some similar pattern. It will like just do it for them.
You could do generative Python coding.
I mean, yeah.
Well, I'm actually just going to type it. So, and then we need max n-gram. That's going to be an integer, and that's going to be the longest an n-gram can be. And in practical applications, you probably won't have very many n-grams of that length actually show up in your vocab, but you can have cool things happen, like it learns like full phrases and cool stuff like that. And this is going to actually give us a generator, but I'm lazy, so I'm going to say it's an iterator. So we need to have a sliding window and then have another sliding window on top of that. So we're going to say for start IDX in range len text, and then for end IDX in range. What do I want this to be? Start IDX to, and then it has to stop at either the end of the string or the like start ADX plus max n-gram. So you say min start IDX plus max n-grams, max n-gram, or len text. And then we're just going to yield text start IDX. And I think we want to add 1 to end IDX actually. So
this combo.
Oh yeah, so if you type really fast, like really furiously, then it's telling you like, yeah, you're killing it. Yeah, there's also like a corgi mode, but that's a little bit too extra.
That feature on? Is that like
yeah, I think you go to like tools settings. No, this is very important. Yeah. Some power. I can't do full power. Full power is too much.
Vanilla Jupyter.
No, this is collaboratory.
When is Google killing?
I don't know, man. Free GPUs in the cloud. Somehow that hasn't already been killed. So let's test this out a bit. A, B, C, D, E, F, G. And we want n-grams up to length 4. So if this is right, then yeah, that looks right. Okay, cool. So we have generate n-grams. So now we want to essentially, for each text, generate the n-grams in it, count each of those n-grams, prune it, and then return the vocab. That's how we want to do it. So I'm going to write the prune vocab thing first, because that's kind of trivial. So we have, thank you. Counter, prune to, which is like, that's how much we're going to reduce it to. and that's going to give us another counter. So first we want sorted counts. That'll just let us say, okay, we're going to take up to the top, the top n counts, and then just return those. So equals sorted vocab.items, and then key is the sorting function, and p, negative p, because we want it to be descending. So then from that, we just have to rebuild our vocab from that. So we're going to say counter, dict, sorted counts. You also have to actually limit those, otherwise it's not going to do any good. Yeah, I think that's it. And this is essentially, sorted counts is a list of tuples, which is the key and value. And if you just pass that straight to the counter, it's going to count those. And you're going to get a really weird result. So you got to pass it into a dictionary, which knows how to interpret pairs like that, and then build a counter from that. So let's try this out. Let's prune a fake vocab A1, B2, C3, D4, and we're going to print it to 2. Yep. This is, hey, there we go. So not that impressive, but at least we know it works. And the last one here for generating our vocab, we want to just count vocab. We're going to get text in there, which is going to be a list of strings. Max ngram, because we got to pass that to our ngram generator. And prune2. And prune2 is important if you're handling a lot of data, because you will run out of memory, like very quickly. So got to initialize our vocab equals counter. And for text and texts, for ngram and generate ngrams of text max ngram.
You missed the end of max ngram on the properties, or the signature. The signature there.
Max gram. All right, thank you. So, and then we just increment that, and for each text we check. So this is where we say, like, is this getting too big? If len vocab is greater than, like, let's say like 5 times prune2. That's like a rule of thumb that I've used, that the more often you prune, you kind of waste more time doing it. Because this is, you're literally reconstructing the whole vocab, which there's probably a faster way to do it, but you can overshoot it a bit and then just go back down. Vocab equals prune vocab prune2. And then we're just going to return that afterwards. That looks right. Syntactically fine. So I'm just going to cheat and grab some example data up here, because I don't want to type out all the sentences.
Come on.
Then I have to remember them. So yeah, so that's our fake documents up here that we're learning from. Normally you'd have a lot more. They might be longer, etc. And this is completely without any language knowledge of the language. So you see spaces in there, you see places where it's cutting across word boundaries, and honestly that's fine if you have enough data. So this is the vocab, and it kind of, you look at it and you're like, okay. I mean, there's a bunch of things that are 1, that's interesting. With sizable data you wouldn't run into that. But let's see what it does. Encode vocab. This is how we do it. Throwback 90s. 12, I think it was. Yeah. So you can see here how it learns these subword parts, right? It never saw a capital T this. It saw lowercase t this. So it just replaced that part, and it saw enough ngrams of his, I guess you could call it, that it can replace that and learn that directly from the data. It learned do, HOW, okay. And also you can see where sometimes the greedy encoding can be problematic because it is probably something that's in there also, but it's starting with a space there because we haven't removed those. We haven't imposed our knowledge of English on it. So you can see that works. This is like, it's got to be like, wait, I didn't implement encode. Oh God, do you guys want to see that? Okay. Let's just pretend this didn't happen.
Where did it get imported from?
No, I did all this stuff. So I practiced beforehand.
So it's running in the...
Yeah, and I didn't restart the instance.
It's in the kernel, like hiding somewhere.
Yeah.
Basically, that's cute.
So def encode.
Just don't restart it.
Yeah. I should have, honestly. Oh well. So vocab. Let's start with vocab. That's going to be like a counter is technically a dictionary, and splitting hairs there, but we got our text that we want to tokenize, and then we want the max engram that we want from it. And that's going to give us just a list of tokens. So we're going to need a list. Let's make that. We're going to need to track a position throughout the string that we're handling. And I think that the way that we want to do is we want to say while current position is less than len text. So like until we've handled the whole input string, we want to keep going. And then for each time that we try, we want to start with the longest possible substring and see if that's in the vocabulary and potentially omit it. So for, let's say I in range max engram 1, -1. So that's going to be, that we're going to iterate backwards from our maximum engram length to 1, which is our minimum engram length. And then just say, okay, engram equals text current position to current position plus I. If engram in vocab, then we just want to, cool, mission successful. Tokens append engram. Current position gets the length of the engram. Or I can just say I, can't I? Huh? Oh, see, misspellings. You guys are saving me. Huh?
That's okay. This is what this is for.
Yeah, right. We need that in the Python interpreter. That would be a terrible idea. And I think that's it. Oh, so one thing we do have to do is if the token, and this is kind of cheating because the vocab should include all of the tokens you're going to see, or you make some rule around it, but we're just going to pretend that it doesn't necessarily. And if there's a single token we see, or if we don't manage to find that token or that character in our vocab, we're just going to say that it's that anyway. So we're going to add a little flag here called handled. And then we're going to say handled equals true. And then break. And then at the if not handled tokens.append text current position, and then we're just going to increment that. Then yield the tokens. Ooh, return. Okay, so let's see if we get the same result. Yeah! So as you can see, less than like 30 lines to do all of this stuff. So it's obscenely simple to implement this. And honestly, this same strategy, with given more data, actually does something much more impressive. Where so you saw that piece of Japanese text. How do I tokenize this from before? And I promised that this was useful when you didn't know anything about the language. So I got about a bunch of Japanese Wikipedia, and I took about 250,000 articles and just fed it through there, learned a vocab from that, and told it, okay, do it. And you can see here that it's, maybe you can't read Japanese, but these are actually like meaningful chunks right? Koreo, it's like this, acting on this. Token, desktop, like there's all these things in here. It's a pretty decent tokenization considering that it doesn't know anything about the language itself. And it learned all of this unsupervised from unlabeled data, just pulled from Wikipedia. So BPE is great.
Like learned as in like I applied like this pretty much compression algorithm to
Yeah,
it, and
yeah.
I got like meaningful.
I think there's an argument to be made there. Maybe machine learning is just compression in the context of a problem.
Sure.
That's
Do any algorithms leverage existing, basically use that compression as a base point and then just go from there?
so using like compression as like a framework of problem solving, definitely. Like autoencoders it's this idea that we should be able to create an information bottleneck, which is essentially compression, and then the network will learn what ways that it can compress the data without us having to know anything about it. Those are pretty cool. I don't know. There's some learn to compress stuff also, but I don't know if there's any that really sit so close to compression as BPE does. I think other ones are just
vectorizing words is compression.
Yeah.
Too.
Yeah.
I know when they do DNA sequence analysis, they actually just work directly with the compressed data because it's so much easier to work with.
Really? Not like zipped, is it?
It's zipped.
Oh God! Wow.
It's whatever compression they use. So it basically saves a lot of data, and it's actually faster because
it's probably similar to word vectorization because you would take sequences common sequences of DNA and then encode those to a numeric value or something.
Yeah, I love where you guys are going with this. By the way, this is great. Any questions about the implementation before I shortly go back?
Just a quick question. I was wondering, have you compared, so this where we go from the beginning of the word versus going from the end of the sequence, and seeing if we get the same words in both instances?
This is, even though I went from the longest possible one inwards, it would get the same result. It's just that made it easier to code live. It's the question really comes down to, are you likely to find more words or more final subword tokens that are shorter rather than longer? And I didn't really do any benchmarking on that. So, but good question. All right, so I'm just gonna go back for a second to scratch my head a little bit about this. It struck me when I was reading through these and looking at the BPE implementation that BPE looks a lot like phrase extraction, a lot, because you're essentially going through counting n-grams. Scoring them somehow in BPE. It's really simple. And then you're exporting a model that has collections of valid n-grams or n-grams that are worth using, right? But in phrase extraction, they've done a bit more looking at, how does scoring affect the quality of this model? I think one, because it's easier to directly inspect the exported model. You can look at phrases. Are they meaningful? But can we, should we be applying a more complicated or more nuanced scoring phase to learning BPE vocabs? Are there more intelligent ways to judge if a piece of the vocabulary is actually good? Things like mutual information that were really useful for changing how you do phrase extraction. Or using partition data sets, which can help you learn phrases or BPE vocabs in context of partitions in your data that you know about. And even more abstractly than that, looking at these different types of data, is there something more non-language related that we could do to make a general tokenizer, where we have some knobs, but it is ostensibly looking through the sequence and scoring, continuous spans of characters or bytes or what have you. Why are there ones that are language specific? It's really tempting to think that there's something out there that maybe isn't the best for size compression or speed compression, but is for meaning or information as it's useful for a predictive model compression. And that, once I get to that point, it's like, ugh. There's a little bit too much to think about there. But hopefully, that's a thought you guys can go forward with. But yeah, questions?